This is the review of molar mass and percent composition for the students in my pre-AP Chemistry 1 class that missed on the dates of March 2nd and March 3rd. Use this video in conjunction with the empirical and molecular formula video on my website to catch up with any material that has been missed. Alright, so by the end of this video, I would like you to be able to calculate molar mass and percent composition using the chemical formula. Also, if given the chemical name, you should be able to determine the chemical formula at this point for ionic and covalent. So to start off with, we are going to look at percent composition, but we're really going to be looking at molar mass and percent composition at the same time. Mass and percent composition. Because in order to determine percent composition, we have to know molar mass. Alright, so let's get started. Given the formula KMnO4, potassium permangate, what do we already know about this compound? Well, we can look at the periodic table and determine that potassium has a average atomic mass of 39.098 or 39.10 grams per mole. Manganese, we can look at the periodic table and determine that it has 54.94 grams per mole. And oxygen has 16 grams per mole. Now, looking at the chemical formula, we also see that we don't just have one oxygen, but we have 4. So in order to get our total mass of oxygen, we need to multiply this entire unit by 4. And that will give us our grams of each. Now to find out our molar mass, the molar mass is going to be the sum of all elements involved in the compound. Alright, so now the next thing we need to do is determine what our molar mass of KMnO4 is, potassium permangate. Alright, so to calculate potassium permangate's formula mass, we're going to add 39.10 plus 54.94 plus 64 grams of oxygen, and we should get 158.04 grams per mole. Now, to determine percent composition, we are going to take the mass of the element divided by the molar mass times 100, and that will give us the percent composition for each of these. So I'm going to go ahead, set up the equations that we have, and then we will then give you a minute to solve. That is for potassium. For manganese, it's going to be 54.94 divided by 158.04 times 100. And then the last one, oxygen, will be 64 grams divided by 158.04 times 100. Sorry. Times 100. All right, take a moment and solve for each of these, and then we will come back and check our answers. All right, when we solve these, for potassium, 39.10 divided by 158.04 molar mass of potassium permanganate times 100, we should have come up with 24.74%, depending on how you round it. I like to stick to 2 decimal places when I'm doing these, just for cleanness sake. For manganese, 54.94 divided by 158.04 times 100 gives us a percentage of 34.76. And with oxygen, 64 divided by 158.04 times 100 gives us 40.50% after rounding. And as with any percent composition, when you total up the percentages, you should get pretty close to 100%. There is a little bit room for error depending on if it's experimental data or just given data. Sometimes you might come out like 99.9 or 99.8. You just want to be within pretty good range of 100%. All right, I'm going to do one more of these with you, and then let you look at, and I'll show the whole sheet for you to do on your own. So let's look at, let us look at number 5, aluminum sulfate, and do the calculations from there. Alright, so pause the video, take a minute, and determine the formula mass for aluminum sulfate, and we will go from there. Alright, so beginning our calculation for molar mass, we see that aluminum has an atomic mass of 26.98, and there are 2 aluminums, so we multiply that by 2, which gives us 53.96. Sulfur has an atomic mass of 32.06. There are 3 sulfurs based on distributing this 3 inside the parentheses, so 3 sulfurs, 12 oxygens. That gives us 96.18 for the mass of sulfur in this compound, and the mass of oxygen, oxygen's atomic mass is 16.00, and there are 12 oxygens. 4 times 3 is 12, which gives us 192. And to determine the molar mass, we will now sum 53.96 plus 96.18 plus 192. When we do our calculations summing these, you should come up with a number of 342.14 if I did my math correctly. So that gives us an atomic mass of aluminum sulfate of 342.14 grams per mole of aluminum sulfate. Now, next step is to determine percent composition. So again, it is the element mass over the molar mass. So we will do this for each of these. For aluminum, we have 53.96 divided by 342.14 times 100. Then we will do it for, so that's for aluminum. For sulfur, it's going to be 96.18 divided by 342.14 times 100. And then lastly, we have oxygen, which is 192 divided by 342.14 times 100. Take a moment, pause the video, solve for each of these, and then we will move on. Alright, when we do our calculations, we find out that aluminum, 53.96 divided by 342.14 times 100 should give you a percentage of 15.77%. For sulfur, we should come up with 96 divided by 342 times 100 is 28.11%. And oxygen should come out to approximately 56.12% by taking 192 divided by 342.14 times 100. Now, again, as I said before, when you total these up, should come pretty close to 100. In fact, this one will equal exactly 100, as well as the other that we did. Now, what I would like for you to do, go ahead, take a moment, and I want you to do the percent calculations for HCl, manganese nitrate, so number 2, number 3, and number 4 from this sheet. You may have to copy these down on a separate sheet of paper, whatever you need. I will put the answers up, but you need to go ahead and pause the video now, try to work these out, and I will, in the next few seconds of video footage, I will post the answers. So please pause now. Alright, so when we do number 2, we come up with 2.77% hydrogen and 97.23% chlorine. Again, coming up 100 or really close to 100. Alright, so for magnesium nitrate, we come up with the following. For magnesium, we should get 16.39%. For nitrogen, we come up with 18.89%. And for oxygen, we come up with 64.72%. And then lastly, we'll do ammonium phosphate. Alright, finishing up the final equation, ammonium phosphate, we end up with 28.19% nitrogen, 8.13% hydrogen, and 20.77% phosphorus, and 42.92% oxygen. Now, when I total these up, I end up with 100.01%. So just realize that when you round things like that, you can come up with a little bit of error, but this is not so far off that we can that makes that wrong. I suspect I had a rounding error in nitrogen or oxygen. when I did this. Okay, so that concludes our lesson on empirical, not empirical, but molar mass and percent composition. I am going to throw in some information of, well, what do we do with this molar mass? What is it used for? What is the percent composition for? We see where percent composition is used in reverse for determining empirical formula. But what we're going to have to find out also is what other information can we use this for? And the other information is going to be converting from grams of an element to moles of an element whenever we start dealing with empirical formulas and determining molecular formulas. So along with this video, I will also include another video that's talking about converting from grams to moles, moles to grams. Thank you. Alright, so this is part 2 of the review video in preparation of solving for empirical formulas. We've already discussed percent composition and molar mass. Now we are going to look at how do we determine the number of moles when given the number of grams of a compound. So what are the tie-ins, what are the connections of this? So in order to determine the number of moles, to go from moles to mass, we still need to know molar mass and we need to recall that solving for molar mass, we just total up the masses of the elements in the compound. So for example, sodium chloride, we need to get the sum of all the sodium atoms, or the sum of the mass of sodium atoms plus the sum of the mass of the chlorine atoms. So sodium is 22.99 grams and chlorine is 35.45 grams. We only have one sodium, one chlorine in this compound, so there's no other things we need to do here other than just sum the two. When we add up 22.99 and 35.45, we come up with a molar mass of 58.44 grams per mole of sodium chloride. Now, to determine the number of moles, we want to determine the number of moles of each compound. So we are given, this is our given, that we have 25 grams of sodium chloride. Now, looking at it just visually, 25 grams is less than 58.44, so that means we are going to have less than 1 mole of sodium chloride. And again, we can do this through using basic stoichiometry. We have 25 grams sodium chloride. We want to set our equation up so that we are canceling out grams. So we're going to place our molar mass on the bottom, which would be 58.44 grams for every 1 mole. That means that grams cancels, and we are left with moles NaCl. 25 divided by 58 gives us 0.4277891855 moles. We have to look back how many sig figs were we given. We were given 2 sig figs, so we can actually say that this is 0.43 mole of sodium chloride. All right, we'll do this with one more. Let's go ahead and do it for potassium. let's do it with one that has subscripts involved. So we're going to look at hydrogen is going to be 2 times 1.01, which gives us 2.02. Sulfur, we only have one sulfur, so sulfur's atomic mass is 32.06. And oxygen, we have 4 oxygens, so that's going to be 16 times 4, which gives us 64 grams of oxygen. All right, now we just have to total these to get the molar mass, and we will do that. So for the molar mass, I come up with 98.08 grams per mole. So to determine the number of moles of H2SO4, sulfuric acid, we will take our given 125 grams times 1 mole over our molar mass, because it's grams per mole, 98.08. So essentially 125.98.08. This number is larger than this number, so we're going to expect it to be larger than 1. So we end up with we only have 3 sig figs because our given is in 3 sig figs, so we'll go 1.27 mole of sulfuric acid, H2SO4. All right. Go ahead, try number 3 and number 4 on your own. Pause the video, and I will post the answers in a few seconds. Please pause now. All right, so finishing out number 3, if we have a 100-gram sample of potassium permangate, molar mass of potassium permangate is 158.04. We determined that earlier in this lesson. So 100 grams divided by 158 gives us 6.633 mole of potassium permangate. And for number 4, if we're given 74 grams of KCl, and when we do the math to solve for the molar mass, we get 74.55. So that is 0.99 moles of potassium chloride, or essentially 1 mole of potassium chloride. Now, after you've watched this video, you should have the basic skills to be able to solve an empirical formula question. Watch the video for empirical formulas, look at some of the examples, and go from there. One thing I will say, and I'm going to go ahead and add one slide, and I will just give you some conversions for going from moles to grams and grams to moles. Just some simple setup equations. All right, so sometimes you'll have to convert from moles to gram. So when you're given information in moles and you want to convert to grams, basically it's going to be given number of moles over 1 times molar mass over 1 mole. The idea here is we're wanting to cancel out moles and be left with grams as our unit. Now, more often than not, when determining empirical formula, we're going to be given information in grams, and we need to go to mole. So from going from grams to moles, we'll have our given in grams, given mass in grams, over 1 times, we're going from grams, so molar mass will go on the bottom, which is in grams, one mole over the molar mass, and then the grams cancel, which leaves your answer in moles. So, and then this one would give you an answer in grams. All right, these are the basic conversions that you need. If you can get there, you can pretty much get any number that you need from that point. Next unit after midterm, when we start stoichiometry, we'll take this another step and start doing multi-step dimensional analysis, multi-step stoichiometry. All right, hope this helps.